Andy is working with the AAPP. We're actually in the pleasure of having two talks in today's seminar, one by Andy Menking and the other by David Etheridge over there. And we discussed making it up. Actually, Andy is primarily at Aspendale at the moment, but I guess next year sometime you'll actually be here in Hobart permanently, working with the AAD in particular, but located here in the AAPP at IMAS. So Andy is going to talk about using carbon-13 to understand past CO2 variations in ice cores. And David will be the follow-on act, and he'll talk about trace gas emissions over the Anthropocene in reducing the oxidizing capacity of the atmosphere. We're actually a bit lucky to have these two gentlemen from CSIRO Aspendale talking to us, but actually reflects the fact that the AAPP is a partnership of both Bureau of Meteorology, Geoscience Australia, the Antarctic Division, CSIRO, and the university. So welcome, Andy. Welcome, David. Introduce yourself.
Thanks, Nathan. Yeah, I just really wanted to say thank you so much. It's been an awesome, warm welcome to be here, and it is really, really great to talk to people in person. It's not something we've got to do a lot of the last couple of years, of course. Really good to be on the continent also. So yeah, so David and I are here until Friday, and one of the main reasons to visit was to introduce actually myself and to sort of broadcast a little bit what my research interests are. I'm going to talk mostly in this talk about using carbon-13 stable isotopes of CO2 in ice cores to study past CO2 variability and what C13 can tell us about CO2 changes. I'm going to add in a few words at the very end about what I'm working on at CSIRO and Aspendale. But most of this work is going to have to do with stuff I was actually really interested in during my PhD. Yeah, so I'll put in some more plugs at the end about coming to chat with us about similar interests and that sort of thing. But I think I'll just jump into it from here. So what's the motivation for studying trace gases in ice cores? I've plotted here the sort of modern day rise in three very important greenhouse gases: methane, nitrous oxide, and carbon dioxide. I've also plotted the temperature warming, the annual temperature anomaly from NOAA at the bottom. That is a result of this rise in the greenhouse gases and the induced, of course, added greenhouse gas effect. But some of the, I should say that most of the rise, we all know this, I think, in this room, but most of the rise in these greenhouse gases is attributed to anthropogenic emissions, land use changes, basically things that humans do today. But some of the rise is due to natural feedbacks that actually result from the warming itself. And parsing out what those processes are and how they respond to climate versus what is the anthropogenic effect is a very tricky business. Ice cores are this very unique geological archive that allow us to look back in the past, make direct measurements of what is, in my mind, literally fossilized atmospheric air, and put these kinds of major modern changes in context. It also allows us to isolate natural processes, to look back way before humans had the influence they have. So there's a bit too much on this figure, I think, for this short talk, but I'm just going to give a real down and dirty view of some of the changes that I'm interested in these trace gases in the past. What I'm plotting here is ice core records of a few different things. This is looking back from about 135,000 years ago up to 10,000 years ago. And what's plotted here, do I actually have
Use the mouse.
Use the mouse. Just wiggle it around.
Yeah.
Okay, great. So the top is Antarctic temperature. Below that is CO2 concentration. These are all ice core records. This is Greenland temperature plotted in the middle, also in black, methane and nitrous oxide. Basically, what I want to highlight with this slide is that we're really looking at two main modes of variability. On the one hand, we're looking at interglacial variability. So this warm period back here, 130 to about 120,000 years ago, is the last interglacial when global temperatures were relatively warm. And then the descent down to colder temperatures is essentially the glaciation until we finally arrive at the last deglaciation, which is pictured here when Antarctic temperatures rise again. CO2 basically goes, well, I should say all greenhouse gases basically go lockstep with these glacial interglacial changes. If we were to look back at the long record, 800,000 years back, you would see high greenhouse gases during the warm periods, low greenhouse gases during the ice ages. But that's not the only mode of variability. There's also superposed on this kind of high to low, warm to cold changes. You see millennial scale variations, which are these wiggles that happen during the cold intervals, actually. CO2 generally goes sort of lockstep with Antarctic temperature, and these changes are largely thought to be due to ocean processes. Methane basically goes lockstep with northern hemisphere or Greenland temperature, and those changes are largely thought to be due to hydrologic changes that are enacted by very large scale ocean circulation changes that are driving these temperature fluctuations. And so those actually cause atmospheric subtle connections that alter the hydrologic cycle and can actually zap methane source regions into action and make big changes in the atmospheric methane burden. Nitrous oxide comes from both and actually exhibits kind of both of those variability. It looks a little bit like CO2 in some cases, and it looks a lot like methane in other cases. I'm actually in this talk not really going to talk very much about methane or nitrous oxide. I'm going to mainly focus on CO2. And my goal is to hopefully by the end of the talk convince you that delta C13 of CO2 or carbon-13 isotopes of CO2 can add a lot of information to understanding what exactly is going on to drive these changes in the carbon cycle. So delta C13 of CO2 is a tracer of the global carbon cycle. Atmospheric CO2 is essentially controlled by different carbon cycle processes, which I think is still very well illustrated by this now somewhat old IPCC figure of the carbon cycle. So the red arrows are the anthropogenic fluxes. For the purposes of paleoclimate studies and paleo pre-anthropogenic CO2, we can largely ignore those. What we're really interested in then are the black ones. And so these are exchanges between the terrestrial biosphere and the atmosphere, exchanges between the ocean and the atmosphere, but also internally reorganization of carbon in the ocean as well. I've also labeled these different reservoirs with different delta C13 values. The atmosphere, at least pre-industrially, tends to be around minus 6.5 per mil. The ocean tends to be more enriched with values in the surface 1 to 2.5, getting lighter in C13 at the deep ocean. That's because of marine biology exporting organic carbon to the deep ocean. The terrestrial biosphere tends to be quite negative or quite light, as we say in geochemistry, with very low delta C13 values. The reason these reservoirs are different is because of physical and biological fractionations during transfers of the CO2 into these different carbon reservoirs. The delta C13 of CO2 in the atmosphere is what changes as these different sources and sinks change the relative weight on that atmospheric burden of CO2. Another way to say it is it's the sort of flux weighted average of the carbon isotopes that are coming in and out of the atmosphere. So as these arrows change magnitude, we expect C13 to change. We can reconstruct that in ice cores and hopefully infer what was going on that caused CO2 to fluctuate. But then actually attributing these changes with a C13 record from ice cores becomes pretty complicated pretty quickly. This is my and others' effort in hopefully simplifying this to some extent. So what you're looking at is in this large plot is the expected change in delta C13 of CO2 and the expected change in CO2 concentration for a given perturbation or a given individual change in the carbon cycle. So just a couple of examples that hopefully might make sense. I think one of the easiest to understand would be land carbon loss. If you do a rapid oxidation of organic carbon from the terrestrial biosphere, release it to the atmosphere, you're going to be releasing stuff with a very negative delta C13 value, very light isotopically, which is going to drive delta C13 to more negative values while increasing CO2. And that's why it looks like this vector. If you increase the efficiency of the biological pump, the ocean biological pump, say by either increasing biological productivity in the ocean or changing ocean circulation in some way that ventilation of that respired carbon is not able to make it back to the atmosphere, you will actually decrease CO2 and you will enrich the atmosphere isotopically. So you'll make the atmosphere heavier. Sea surface temperatures also have a temperature-dependent fractionation. So as you raise sea surface temperatures, less dissolved CO2 can exist in the surface ocean, and you also get a temperature a change in the fractionation, the equilibrium fractionation that's a function of the temperature change, to actually enrich the delta C13 and also drive up CO2. So these are just examples of the way I think about individual perturbations and how they might look in terms of their impact on delta C13 and CO2 when I reconstruct them using ice cores. The last thing I'll say about this is just that this diagram comes from a bunch of idealized experiments with the box model that essentially accounts for equilibration of these perturbations of CO2 with the ocean and the terrestrial biosphere. So it's a very important component of this. This isn't just putting C13 and carbon-12 into a jar and mixing between two simple end members. There are these reservoirs that are influencing at the same time that you have to account for it. And so this model is able to do that. An inherent limitation of interpreting delta C13 this way is that there's not really an inherent reason why only one of these things should happen at a given time. If CO2 is changing and you have a combination of these things going on, you would expect some kind of, in my opinion, linear combination of these vectors acting together. And so there's a real limitation that you can't quantitatively use C13 and CO2 to attribute exactly how much CO2 to a given process here, because you can't ever, at least on these glacial and interglacial timescales, rule out that a bunch of different stuff is happening. But hopefully, I'm going to convince you that it still adds a powerful constraint and a lot of useful information. Okay, so before I get into any data, I want to just talk about a very interesting ice coring site where I spent 2 field seasons during my PhD, which really has added a lot of power to, because of the way we can collect these ice samples of this glacier. It's really improved the data in terms of these stable isotope studies. So Taylor Glacier is an outlet glacier of the East Antarctic ice sheet. Snow accumulates at Taylor Dome and then flows down this northern flank to basically Taylor Valley. And Taylor Glacier winds through Taylor Valley and the McMurdo Dry Valleys and essentially terminates about here in Taylor Valley. Because of a combination of sublimation of the ice at the surface and folding that's happened to the ice as it's flowed through this valley, old ice is actually at the surface of the glacier, and actually very old ice is at the surface, dating back even to the last interglacial period. And what's really cool is that ice in certain places of the glacier is actually turned vertically. So when you drill to depth, you actually can collect nearly infinite amounts of ice that are the same age. And that's an incredibly powerful thing in ice coring, incredibly unique, because in order to get old ice, it usually takes at least a multi-year effort of deploying a deep ice drill to a site. And then when you get to this really valuable time period, like the last deglaciation or like one of these lineal scale changes in CO2, you don't get a lot of ice in that effort. So you're sample limited. In this case, we can go out to the glacier and we can get like massive amounts of ice core, bring it back to the lab and do all kinds of repeat analyses on really large amounts of air. So that's really why I think this kind of horizontal ice coring or this surface ice coring is really valuable, particularly for this trace gas stuff. This image over here is really cool. This is a high contrast image from above the glacier. the different colors that you see are actually different stratigraphic layers of ice with different amounts of dust loads. So this really purple band here is the last glacial maximum. If you were to walk in this direction, you actually go through some of these Heinrich Stadial and Dansgaard Oshker events, and there are higher and lower dust loadings in the ice. If you go the other direction, you essentially go through the last deglaciation and into the ice. So as you walk along the glacier, the age of the ice below you is literally changing. Pretty cool thing. We exploit this dramatically. We take a really massive diameter, what we call a blue ice drill, to the surface of the glacier, and we drill pretty much around the clock for 2 months straight. And we collect meter-long cores that weigh about 50 kilos each. And in some cases, that entire core can come back to the lab. We're usually cutting it up on the field, sampling it, taking back smaller sections. We even take a gas chromatographic lab to the glacier. We make methane measurements on the ice within a day or two of recovering it from out of the glacier. And the reason that's important is because the methane concentration, distinct changes in methane concentration in the past can be related to published methane records that have pre-existing age models. So we can get real age information within like a day or two of taking the ice out of the surface of the glacier to inform, where we're going to collect more or tweak sort of our sampling. This is just an example of doing this out in the field. So like the purple line is continuous methane measurements measured on a Picaro system with a melt extraction system that was installed in the field. I guess the goldish brownish markers are gas chromatography measurements of methane. And you can essentially build these records on depth in this case out of the field, and then relate these with typepoints to pre-existing records. You basically get like real-time reconnaissance age information. So that's the strategy for dating the ice out in the field and for getting a whole lot of it. We take it back to the lab then. We extract the ice in a dry crushing system. These are called cheese graters because they kind of resemble the abrasive surfaces of cheese graters. They're basically vacuum chambers. We shake the ice violently inside, and it pulverizes the ice and releases the air bubbles into the vacuum without altering the composition. The CO2 can be extracted from the air at liquid nitrogen temperatures by condensing it on stainless steel. And that CO2 from your ice core sample can then be measured on a gas isotope ratio mass spectrometer. This yields really, really good precision measurements, mainly because we get a lot of air from this glacier. They're big samples that we can extract air from. But as I said before, we can also resample and resample and resample ad nauseum and get really good replication that makes good statistics. Okay, so I'm going to finally show some data. Here, I'm basically showing 10,000 years back to 80,000 years. This is a snapshot of the last glacial period. And I'm showing in purple these data from this glacier where we've really been able to improve on the precision and add a lot of information to the story of what delta C13 of CO2 was doing in the past. So that's true for the last deglaciation record, which is here. So when CO2 rose about 80 ppm, we have a very, very tight, precise record of delta C13. We also have this for one of these millennial scale oscillations in CO2 that I mentioned in the beginning of the talk. What I'm mostly going to focus on from here on is this record here that I spent a lot of time developing as part of my PhD. And this actually brackets a really interesting period of time called the marine isotope stage 5-4 transition, which is a global cooling interval that I'll talk about in just a second. But basically, CO2 dropped about 40 ppm in a pretty paleoclimate speaking short period of time, like 3,000 years or so. And the question I got really interested in, where did the CO2 go, and can we trace that with carbon-13? I don't want to. So I also showed the brown data set. I don't want to leave the impression that like I dislike that group. That's from the Swiss group. That's the burn data set. It has a very powerful advantage that they have a continuous ice core record of C13 that spans basically the last the penultimate deglaciation all the way through the last deglaciation. They can look at changes continuously, but they do a fundamentally different kind of mass spectrometry. They have very small samples that yield small amounts of air. I also know anecdotally they've had a lot of problems with drill fluid actually contaminating these isotope measurements. And I think the result is pretty apparent. They're able to get a lot higher resolution data with a lot tighter precision. And it adds a lot more information, which hopefully I'll convince you in the next couple of slides. So focusing in on this period here from about 74,000 years to 60,000 years. This is the main thing going on is the marine isotope stage 5-4 transition. It's this global cooling interval. This is a period of glaciation. Sea level decreases substantially to nearly last glacial maximum values, but not quite. Sea surface temperatures are cooling. There's a lot more glacial dust coming from South America that's potentially causing iron fertilization in the Southern Ocean. That's a potential source of reason for drawing down CO2. There's also significant increase in sea ice extent in the Southern Ocean. This stuff is all traced in these various paleoclimate proxies. It's a very interesting period of time. And again, I'm mostly focused focused on this 40 ppm drop in CO2 that you can see down here. But as you'll see, there's actually more nuance to the data set that I'll get into. So presenting this data set, so what I'm showing here is North Greenland ice core temperature, the water isotopes according to temperature, and Arctic temperature is below that. The red data are new data that I've measured from these large volume Taylor Glacier samples. And so in the red data here in this trace is CO2 concentration overlaid on the existing records. The record below is the delta C13, also shown over the data from the burn group that I just talked about. Below that actually is a reconstruction of mean ocean temperature, which actually, oddly enough, comes from ice core air bubbles as well. I'm not going to talk very much about that, but the group at Scripps does a lot of this. You can actually understand mean ocean temperature changes by measuring noble gas changes, because the amount of noble gases in the atmosphere is relatively unaffected by processes except for physical ones. And temperature changes in the ocean cause the different noble gases to dissolve at different places, different proportions to each other. So they're able to back out mean ocean temperature that way. But I just want to talk about the C13. So I've divided this record into 4 intervals based on the CO2 changes that I see. The first is about a 10 ppm rise in CO2 that is almost exactly in phase with the Northern Hemisphere warming expressed as DO19 in Greenland ice cores. So there's a rapid warming in the Northern Hemisphere. CO2 has this uptick. C13 gets more negative by about 0.4 per mil. That's a really, really big change. That's actually almost as much C13 change as was resolved in the last deglaciation when CO2 rose by 80 ppm. Here, CO2 only rises by 10 ppm, so we get about the same isotopic change. The next period, interval 2, is even weirder. CO2 basically decreases gradually, and C13 does 2 very different dramatic things. First, it decreases by about 0.5 per mil. I just told you 0.4 per mil is a big change, so 0.5 per mil is also a very big change. But even as CO2 then just continues to decrease, the C13 rebounds and increases to levels that are more enriched than they were previously. And that enrichment is actually, these are the most enriched C13 values measured in ice cores to my knowledge. So those are sort of unprecedented. What happens during the main cold phase when CO2 is low is that CO2 basically doesn't change very much, maybe a couple ppm. But C13 again changes pretty substantially. So that's pretty curious. About 0.3 per mil changes in C13, basically while CO2 is consistently low. And this increase in CO2 during what we call the Heinrich stadial 6, or basically the transition out of this MIS4 glacial period, that's accompanied by basically the most enigmatic feature in C13 that anyone's seen in ice cores prior to basically anthropogenic warming. So there's about a 0.8 per mil decrease in C13, which is only rivaled by what's going on today when humans are putting fossil fuel combusted CO2 into the atmosphere, driving it to very negative levels. So what this data set really did, I hope I can express this right. It's just really surprising. The C13 changes are really a lot bigger for the amount of CO2 change than we expect. So how do you interpret this? This is, again, probably a little bit too much on this slide, but I'll show you how I use that kind of modeling framework that I introduced in the beginning to step through each of these intervals and try to attribute changes. So I've put up that cheat sheet that I showed in the beginning that has sort of the vectors showing different changes in C13 and CO2 for different processes. I've also just put the data on that cheat sheet, and I've color coded the data based on the gas age. So the ages start here at 0 CO2 change, 0 C13 change, and toward darker colors, they get older. So what's cool about this figure, or this panel, is that you can start to see how these changes in C13 and CO2 start to look kind of like these vectors that I've shaded with the colors. So it may be that certain processes are really responsible for driving these things at distinct intervals in the whole data set. So for the first interval, the one that's this 10 ppm increase in CO2 and this pretty dramatic decrease in C13, that's shown over here. These data spanning 72.5 down to 72 and then back again to 71.7. And I just realized now, I think I've actually reversed the color scheme on you from this panel to the next view. But anyway, the data get much more negative than they rebound. Oops, sorry about that. I think this basically has to be organic carbon. This is very, very negative C13, delta C13 value released to the atmosphere. It's pretty much looking a lot like increases in what happens when you increase Southern Ocean gas exchange rates in our box model, but also in others. But it also makes a little more sense to me that this might be land carbon loss. And the reason being that I would expect this Northern Hemisphere warming event to enact a faster rate of respiration on land in the Northern Hemisphere. And I think that perhaps a combination of the Southern Ocean gas exchange and the land carbon are the most likely explanation for this. The next feature, when C13 takes this big dip and then rebounds, this is while CO2 is decreasing. This is, if you draw a line from the beginning to the end, this is quite consistent with changes in the ocean biological pump, which are very well expressed in other paleoceanographic records, and we can see some of those over here. Essentially, authigenic uranium in the Southern Ocean. This is a proxy for the amount of dissolved oxygen in the deep ocean, which is basically a function of the amount of expired carbon stored in the deep ocean. This increases over this M-4 period. You also basically have pretty major changes in ocean circulation, which should, it's predicted, stratify the ocean and actually favor storage of CO2 in the deep. You also have marked increases in biological productivity in the Southern Ocean. These things are kind of all, I think, inspiring to enact the biological pump. But what the isotopes are showing you in this interval is that that's definitely not the full story. Because if you just enact the biological pump, you go along this line, essentially that's traced in yellow. But that's not what the data do. The data get extremely negative first, and then they rebound by a lot. And so what I think has to happen is these sort of big C13 change vectors on the crossplot. We have to be potentially releasing negative or light CO2, but that CO2 increase is somehow canceled by like a competing sink. And so what I think is plausible, but certainly up for argument, would be that there's some release of land carbon in the beginning of the glacial, but that the CO2 change is actually net negative because there's a compensated sink, probably in the form of both the biological pump changes as well as increases in the ice in the Southern Ocean. I think I'm going to go through the rest of this a little quickly. The changes during M-4 basically require large C13 change and almost no CO2 change. That's a very, very curious mode of variability, which I think you can only get by things like Southern Ocean gas exchange rates, and something that can modulate that is sea ice extent. So I think what you're seeing is essentially possible changes in sea ice extent modulating the isotopes, but not doing much to CO2. And then this last feature, this very, very negative trend in C13 that I said is only rivaled by the anthropogenic era when we have these fossil fuel emissions driving C13 to low values. That's, again, it's just got to be a lot of change in the isotopes per change in CO2. And the only things that seem to do that are these increases in Southern Ocean gas exchange rate. And that's actually supported by opal flux data. There's actually the second largest feature in this opal flux record that spans through clear the last deglaciation that is actually right here at this MIS43 transition. And so increased upwelling leading to increased opal flux values that could be consistent with the shift in the strength or the position of the southern hemisphere westerlies, which should actually enact faster gas exchange rates and possibly get us along the spectrum here. Okay, so that's yeah.
Open flux, that died on.
Yeah, this is the paper to read would be Bob Anderson stuff about. I think there's actually a great editorial uncorking the Southern Ocean's vintage CO2. So anyway, this is hopefully near publication. This is in review with Nature Communications, and just kind of in that last 95% to get this pushed out. But what I'm trying to do in this paper is be really upfront about the limitations of the method, present the data, and just be upfront. You can't quantitatively use C13 and CO2 when there are this many variables. You really need to be in a situation like the Holocene, which I'll talk about in just a second, when you can rule out a lot of these changes. But for this glacial interglacial kind of stuff, it's a matter of kind of qualitatively cobbling together these constraints and then using support from paleoceanographic data to come up with what you think is the most likely story. So that's it. And then what I'd like to say is just a few words about what I'm working on in Aspendale. So what I'm showing now is the last 3,000 years of CO2 and delta C13 records. Really mainly just from two ice cores. There's the waste divide record in purple, which was measured actually at Oregon State University, where I'm coming from. And then Law Dome, which has about three decades of work from Aspendale behind it. And a lot of what these records have done is there's a lot of sort of interesting periods of variability that are discussed in these papers, but much of this work is focused on the Little Ice Age, which is shown here, which is a global cooling event when CO2 decreased by about 10 ppm. And essentially the chain of logic goes like this. So the delta C13 becomes more positive while the CO2 decreases. And this, you might think, could be because the CO2 is actually sequestered in the terrestrial biosphere. That's what happened, but it's actually known that the biosphere shrank during this time. And so what happened to cause the CO2 to decrease is actually a decrease in respiration rates that's larger than the decrease in the uptake of photosynthesis. So this C13 record, because it gets more enriched, is sort of the rationale behind that, that basically pinpoints the terrestrial biosphere as the cause of the sink. And this period has then actually been used to understand what is the carbon cycle's sensitivity to temperature. And that number actually then gets wrapped into IPCC future projections. And so it's point I'm trying to make is it's kind of an important interval, and these C13 data actually underpin those future projections in an important way. But there are differences between the two records that we have. One really key difference is that in Law Dome, the CO2 change is a lot larger at the onset of the Little Ice Age, and it's basically just smeared over in waste divide, the purple data. Furthermore, we really don't have a lot of data from Law Dome in terms of the C13. What I've done over here, and please take this with a huge grain of salt, because this is really just me playing around with forward simulations in this model, but just asking the question, what do I need to do to the terrestrial biosphere to reproduce the CO2 changes, and then what happens to the C13? Essentially, to reproduce the waste divide data as they are, requires a lot less net uptake of CO2 into the terrestrial biosphere than to reproduce this larger drop in lava. And so then the question becomes, which one is real? Or are they both real, but waste divide is possibly smoothed because of fern and bubble trapping processes? This is basically somehow altered the atmospheric record that it captures. So this is a period of time I really want to focus on at Aspendale with the ice that we can in the Lava Dome archive. And I think it's important that given that these data underpin these projections that we see in the IPCC, I think it's important that we kind of get this right and make these data as good as they possibly can be. So a major target is to see if this huge decrease is in fact real, fill in the isotope record where we have gaps in resolution. We also, there are other intervals I'm not going to really talk about, but basically we don't have Delta C13 data older than about 1.2 thousand years. So looking at these CO2 changes in this period are real, and then what does the C13 do? It's also something I really like to do, possibly with the Aurora Basin ice core. There are also some interesting things to look at actually during the industrial era. We kind of think, at least I kind of think of that as a monotonic increase in CO2. There are actually changes in the growth rate of CO2. We might be able to learn more about what's causing those from more C13. So that's kind of just a little bit of hints as to what I'm getting into at Aspendale. And I wanted to just give an update on the lab. So we have a brand new MAT 253 plus mass spectrometer. It's a very expensive piece of kit. It's now installed at Aspendale. It was an expensive box in a bag with a gantry, and it's actually now grown to a turned on, fully vacuumed, fully operational mass spectrometer that's able to measure C13 concentrations on pure CO2 gas. If you ask me in about 2 months' time, knock on wood, I'm hoping this will be able to measure C13 on CO2 that's actually extracted from ice core air. So that's the part we're still waiting on a lot of parts, but you can see the framing that I've installed. That'll have like tons of valves and vacuum line purification system mounted to it, hopefully in about 2 months' time. Okay, so the other thing this does is measure isotopes of nitrous oxide. I didn't talk about nitrous oxide, but it's something I'm also pretty interested in. So as far as that aligns with your interests as well, I would love for you to come and talk to me. As I said before, David and I are here through Friday. We're going to be in some of the meeting rooms tomorrow and Friday. I would love to talk about CO2, N2O, basic gas isotopes in the atmosphere, marine biogeochemistry, paleoclimate, all this kind of stuff. And the other thing I did say is that this whole system in Aspendale, in about a year and a half's time, knock on wood, is going to be here. So I'm going to bring that here. I'm going to be working here and setting this up for the million-year ice core effort. So we'll be able to do C13 and nitrous oxide isotopes on that ice core. Okay, thanks very much for listening. Really appreciate it. Look forward to talking to you.
Is there time for a quick question?
I'm sure I went over. Sorry.
You might want to come and stand here, David. Back to my set yourself up while taking questions. Is anyone on the chat? Can you see a question from there? Will.
When you're looking at these records and you're comparing the changes in CO2, what's the sort of temporal resolution an average?
Yeah, so it varies between different studies, but in the case of the study I presented, we have a sample of about every 250 years. And we think the smoothing in the ice core is probably comparable to that. So this is definitely not the highest resolution ice core in terms of the actual bubble trapping in the fern. Like the per meter, what kind of time resolution can we get? It's probably somewhat smoothed over because of the low accumulation rates and that sort of thing at the site. But I mean, hopefully the data convince you it's quite sufficient for getting a better view of this. In the case of the kind of ice cores we're working with at Aspendale, what is it, like a year per meter? Oh, so it's like 1,000 years. That's nice work. Yeah, but vertical, exactly. Yeah. So, does that answer your question?
Yeah.
Okay.
We'll run out of time.
Yeah, sorry.
So how do I do the introduction?
Tell me how long, so I'll have to trim this on.
Yes, I think that's probably right, actually, but it may be that there's no actual following date, and it may be that that people are happy to go on. So maybe we'll just work with it flexibly. If people want to walk out at 3 o'clock, do so and see what's left.
Oh, see what we can do in
And
10 minutes.
Vanessa will tell us if there's a lecture afterwards.
Okay. So I thanks for the opportunity, and Andy's introduction was actually, Andy's speech was actually a talk, is a very good introduction, because what I'll present here is similar atmospheric issue, but to do with reactive gases. So nitrous oxide and CO2 tend to be longer-lived, more stable gases, but the reactive gases in the atmosphere are primarily controlled by their removal. And the removal is controlled by the radical that we call hydroxyl. It's produced naturally in the atmosphere. It's what we call the atmospheric detergent, responsible for about 90% of the oxidation within the atmosphere. Very low concentration and very reactive, 1 second lifetime or thereabouts, and very hard to measure. Even present day, it's very hard to actually get a measurement in the atmosphere which is representative of any time and space, because it's so short-lived. So we tend to use what we call integrating traces for hydroxyl concentration. So looking at the atmospheric changes over the last, over the last 100 years, greenhouse gases, within that group of gases, many of the synthetic greenhouse gases and all of methane is controlled by hydroxyl removal. And then on the right panel, the ozone depleters, most of those are also controlled by removal through hydroxyl, except for the CFCs and possibly some within the perhaps carbon tech. But the other gases are removed by oxidation through hydroxyl. So this is a very key compound to the present and past atmospheric composition. And the question has arisen, if we continue, if we have emissions over this period and into the future, will they change the ability of the atmosphere to remove them by decreasing the amount of hydroxyl in the atmosphere? So atmospheric chemistry, very simplistic picture here. In the middle is hydroxyl. It's produced by sunlight and on tropospheric ozone in the presence of water vapor. And it's removed by reacting with those gases we spoke about, carbon monoxide, hydrogen, methane, volatile organic carbons, compounds. And in doing so, it is then destroyed, or it can also be regenerated if the environment has a high level of nitric nitrogen oxides. And at the moment, we would have expected that this removal process would decrease the concentration of hydroxyl in the atmosphere. That's what many of the models are running with when they project into the future, even looking for an emission scenario that would lead to a certain concentration in the atmosphere. The concept of using carbon-14 monoxide as a proxy for measuring the background level of hydroxyl came from the NEMA group in New Zealand. And this is a key paper by Martin Manning and his people in NEWA. The bottom line is that the production of carbon-14 monoxide is through cosmic rays. And there's a certain amount in the atmosphere, and we can measure that in the present day. And we can understand the amount of production using cosmic ray measurements. And then almost all of the sink removal process of carbon-14 monoxide out of the atmosphere is through reaction with hydroxyl. So that leads to a fairly simple approach to quantifying hydroxyl in the present day. And that's what Martin did. He and his group measured hydroxyl over a period, and they're still measuring it now. But this is a period of around about 10 to 12 years. And the middle line there showing variations in hydroxyl from summer to winter as UV produce, variations of carbon-14 monoxide as hydroxyl is removing that more in summer, less in winter. The green curve set shows the cosmic ray variation over that period, which is producing the carbon-14 monoxide. And the bottom panel removes those two influences and looks for a residual, looking for a trend that might be due to changes in hydroxyl. And it shows a pretty steady level, except maybe for two short-term variations. One's in 91 with Pinatubo eruption, and the other is a pulse in carbon-14 CO in 1998, which has been linked to the biomass burning event of that year. And these throwing up a large amount of aerosols, reflecting sunlight, reducing the production of hydroxyl and allowing carbon-14 CO to increase. But apart from that, very little change, which is quite surprising. But it's only a window of 10 years or more. So that the use of carbon-14 as monoxide as a tracer works very well for hydroxyl in the modern atmosphere. And through the action of cosmic rays in the atmosphere, producing carbon-14, oxidizing the carbon-14 CO, and then that being removed by hydroxyl. So to measure carbon-14 CO now, we can estimate that as the hydroxyl as Martin has over the modern period. The question has been, how long has this hydroxyl estimate been steady for? Given that we've emitted a huge amount of gases, compounds which would otherwise pull down the concentration of hydroxyl over the industrial period, has it changed? And we go to the ice. The ice record through the atmospheric samples within the bottles. A complication, though, is that cosmic rays produce carbon-14 CO in the atmosphere, but they also do so through interacting with water molecules in the ice. This is an artifact which needs, or an interference, which needs to be minimised, but also removed from the estimate, and has so far thwarted any estimates to measure it in the past. We, some 20 years ago, almost, or more actually, looking at the carbon-14 within ice, especially with the range of sites we have at Ward showed us that we could probably infer from that carbon-14 monoxide the past OH levels. Now this was implied over 20 years ago, but the challenge has been to remove that in situ component, which is an artifact by the cosmic ray impact on the ice. On the east side of Ward, for anybody who's worked near there, you'll realise it's a very high accumulation rate, and this is the sort of place you need to get a carbon-14 monoxide record, because that in situ production is minimised as the ice is exported very quickly below the surface as more and more accumulation falls. So 1.2 metres of ice equivalent provides a pretty good shielding for the deeper ice from the production by cosmic rays of this artifact. And an estimate here of the comparison between the amount of carbon-14 CO from the background atmosphere. This is the bit we want. It tells us about the hydroxyl, compared to the in situ produced artifact, which increases with depth as more and more is accumulated from cosmic ray exposure. It shows that at DO8, the east side of War Dome, we've got the background atmospheric level much higher than the in situ production. If you look at any other Antarctic site, typical Antarctic site, the background is tiny compared to this artifact because of the much lower accumulation rate. The ice is sitting there at the surface getting irradiated. So roll on some years, and in 2018 and 19, we put together a combined project with the US NSF and the Australian Antarctic Program. Some 10 to 20 people at the site here, on the east side, back at War Dome DO8, and with 3 main drilling activities to pick up large amounts of ice to enable this measurement. And a lot of the measurements are actually done at the site in the shelter here. The first layer that was measured was the fern layer. Air was extracted from the fern in large volumes, and that was allowed us to compare with the atmospheric record. It's the recent part of the record that we can then say from that how much in situ carbon-14 gets produced there and ends up in the fern layer, and allows us to make that correction to get the atmospheric level. The next horizon was drilled by the same drill as mentioned by Andy, the blue ice drill, very large drill to get a large amount of ice from this horizon just in the close-off zone, so we can get ice core air, also with the across the same period as the atmospheric record, to make the correction for in situ ice production. And then the third drill was to extend back in time using 3 deep cores to get the volume we needed for that measurement back to pre-industrial times, or around about 1875 AD. So just quickly, at the site we were extracting and analysing fern air. We were extracting large amounts of ice. So ice core measurers here are trying to get it down to grams, if not less grams of ice for a measurement. We at the site had to measure of the order of 5, or extract air from 500 kilos of ice core. So it's described as ice mining rather than ice core sampling. And this had to be done at the site to minimise the production. As soon as that ice comes back to the surface after drilling, it's getting exposed by cosmic rays. And so the clock starts, and there was no ability to remove it from the site to a laboratory, even at the station, let alone back in Australia, without it being contaminated by in situ production. So the air was extracted within hours of drilling that ice and put into a canister with no moisture, so that that production of cosmic rays on water would stop. This was all done at the site in difficult conditions, very high accumulation, and on the right-hand side there is somebody's living tent after a week or two. Once the samples of air were brought back to Australia, they were then moved on to Rochester, University of Rochester, where Vas Petrenko and Peter Neff extracted the CO from the air and produced a carbon-14 CO2 sample, like in his hand on the right there, which was then sent back to ANSTO for measurement of carbon-14 within that. From 500 kilos or so of ice, we managed to reduce that down to 2 micrograms of carbon, which was the target. So a massive distillation process. Carbon-14 in the atmosphere is a very small fragment of the atmosphere. The total global atmosphere contains about 5 kilos of that compound. We're trying to extract a little bit of that from the Antarctic ice. Fern air concentrations showed us, as we expected, how the fern behaves There's about 25 species there as measured, but also modelled. So we have a very good handle on the enclosure process due to fern air movement. And then the ice core there, going back to 1875 or thereabouts, showing that the concentrations as measured in those samples were as expected. So we had 16 samples, all within the expected range from the modelling, and getting back to pre-industrial levels. Limited time here, so I'll jump across a few important steps, which are actually to use other sites, other ice core sites, to estimate how much in situ produced carbon-14 CO there is within the DO8 site. So there's a fair bit in that, and I won't go into the detail, but a work of 5 to 10 years at these sites by the University of Rochester group has actually been able to quantify that in situ production, so that we can then apply that to the measurements to get the atmospheric level. Now, these are the measured carbon-14, the samples measured. The upper level in the blue being the fern air samples, and then deeper than that, the ice samples. I won't call them ice cores because it was a massive amount. As I say, about 500 kilos for each one of those. And that's the expected increase that we saw back in that model run at the start, where the in situ production is increasing it back in time, but then stabilising as it gets below that zone. Those corrections for the carbon-14 in situ production were applied, and we end up with a data set that looks like this. So starting at the right-hand end, we have the Martin Manning data set, and that is annually resolved, so it shows the annual cycle, and hence the spread in the data. And then in the blue are the samples as extracted and measured from Lord Owen. Now initially in the purple actually is the fern air samples that overlap very well with the atmospheric measurements from the NEWA group, and then moving back into the blue into the ice cores. It's quite a widespread in the age because we had to accumulate a large amount of ice thickness effectively to get those samples. So each sample integrates across many years, but the precision is very good, and over that period we're seeing what looks like almost no change in hydroxyl concentration. The background there's in the red is what we would expect from a stable atmospheric concentration, but with varying production rate, which has been estimated from sunspot numbers. So sunspots can allow you to determine the cosmic ray flux. From the cosmic ray flux, you can work out the production of CO. So it looks like there's been no trend in the observed, measured carbon-14 CO over the industrial period, which is quite surprising. So the conclusions from that, the measurements of 16 air samples from Lord Owen, well, to get them in the first place was actually quite a challenge. And it looks like they came through uncontaminated, sufficient to measure precisely the carbon-14 CO back to 1875 or thereabouts. The carbon-14 concentrations and precisions appear reasonable that we can get from that a record. And from that record, we don't see the 14 CO trend. And the next steps will be to apply some final corrections to those in situ production rates. And now we have a very good age depth profile for the DO8 site from the work done in Hobart on the chemistry and the isotopes of the core. We can refine that correction. And then, of course, we will have a 14 CO record, but we still need to get to the hydroxyl record in the atmosphere, and that will be inferred using a chemical transport model, GEOS Chem. And then we have hopefully a hydroxyl record that can be used to constrain the system's models. access, for example, in Australia, but of course the full range of a couple of models. And an example of why we need to do this is that in the recent, in the last AAPP model comparison, which is the couple chemistry and climate models, we're inferring trends of between -13 and +15%. So they're very unconstrained for their hydroxyl, inferred hydroxyl, which makes it very hard then to predict what the atmosphere will do in the future with a certain emission scenario. So the implication of the result, to finish, stable carbon-14 CO as measured implies stable hydroxide over the last 140 years, which is not expected because the huge increase in emissions over that period was expected to reduce the amount of hydroxide. Now that suggests there's a chemical pathway in the atmospheric chemistry of hydroxyl, which is regenerating, perhaps through that pathway through the NO. But resilient atmospheric oxidation chemistry is good news. It means that future greenhouse and ozone depleting gas concentrations can be more easily managed than if we had a declining atmospheric oxidation rate. It also means, though, that the past emissions, which we've inferred from the concentrations as measured in ice cores, might need revising because those were based on what was assumed to be a higher level of hydroxyl in the past. And just to finish off, to get a global record, the C14O carbon monoxide record from the Northern Hemisphere, I think is needed to complement the Southern Hemisphere result. The Southern Hemisphere is a very clean background environment, and the production and loss of hydroxyl in the Southern Hemisphere goes through slightly different chemical processes compared to the Northern Hemisphere, where a lot of the emissions are and a lot of the background concentrations are high. So the challenge for the glaciologists in the Northern Hemisphere is to find us a Northern Hemisphere Greenland, maybe water dome equivalent, and we'll go through the same process again. I'll leave it there.
Questions for David? Sonia and Ed. Sonia first.
Thanks, David. If we can revise the OH concentrations and then emissions projections or past emissions, has anyone started doing that with just simple emulators, like simple climate models?
Projecting biospheric emissions?
Well, any. I mean, you said it's important for methane, so
Yeah, speaking to the microphone, David, it's
So-
it's still 9 feet long.
So emission scenarios for the future.
yeah, and
Absolutely.
and the
So
past
that's
as well.
within the IPCC CMIP predictions. So emission scenarios, I should say.
Yeah.
And so the biospheric, I think you're talking about, would be in there. And that, I don't know whether the natural variations of biospheric emissions are included, but certainly biomass burning is in there, for example.
Yeah, so I was more thinking like, you've got these really simple climate models like what Malta at Uni runs with, they're basically doing the emissions projections. So can you just plug in the new stable values of OH into that?
Yeah, well, that's a key point because in the same way that CO2 future concentrations have inbuilt a scenario for their loss rate of CO2, the sink of CO2. The future OH levels are within the scenarios for future chemistry, and so this sort of result is what's needed to constrain those models. As I said earlier, the AAPP models give a range over the industrial period of -13 to +15%, a big range of uncertainty. for that period, then projecting into the future, I imagine they would have the same level of uncertainty. These data could be used to constrain those chemistry models.
Yeah.
Sure. So this question comes from a background of knowing almost nothing about atmospheric chemistry. But one of your conclusions was there must be a pathway to regenerate hydroxyls. Isn't that obvious by construction if it only lives for a second? Like surely there has to be a huge pathway generated all the time.
Okay, so if we go to the very start, I think I showed a cartoon, very simplistic from paper 10, 20 years ago. Of course, there's production from ozone on the left-hand side there, and there's loss on the right-hand side as the compounds are pulling that out of the atmosphere. But there's no reason to expect. Well, actually, it's not no reason. There's little reason to expect that pathway from ozone would increase. But maybe you're right. Maybe there is still an opportunity for that to change. For example, the amount of ultraviolet light in the Antarctic has changed as a result of the ozone hole. The amount of water vapor in the atmosphere that's available has possibly changed because we've warmed. And so there's two possible causes there. And of course, because the temperature's increased, then the rate of reaction of a lot of these reactions has changed as well. Whether they're significant, we don't know. But once we have a result like we have, then the models can take that away and say, let's play with these different controls and see if we can simulate what's observed.
David, thanks both speakers for a great talks today. You mentioned in this one here, there's two influences. One from Pinatubo, there's a volcanic influence, and the other one is the sunspot solar activity and the solar forcing. And we see models and forward projections and of organic CO2 temperature, and we then see models that bring in volcanic forcing and solar forcing, and then that helps to explain things a bit better. Do we have a good handle then on the solar forcing and the volcanic forcing, how that might be interacting with the carbon cycle through this process?
Yeah, good question. So this was the Menking result. The residual is what's interesting here. So he's factored out the production rate from the marine curve, cosmic ray production. He's factored out the sinusoid, which is the seasonal cycle, and the residual provides the information on, for example, the first event there, as you said, Pinatubo. So it's that shielding of the ultraviolet light through the particles reduced the amount of hydroxyl concentration production, and the same in '98, which is the bushfires, the Indonesian fires. So the volcanic forcing is if you take that as the cause for that first event, then you've got a pretty good estimate there because the amount of aerosols is known from Pinatubo. And you can see the response. The thing is, though, they're pretty short-lived. So, the volcanoes are there, the aerosols are only there for a short time, and I imagine the hydroxyl will recover after that period. The same with the biomass burning events. The aerosols in the atmosphere that are causing this have a short residence time, compared, say, to the main drivers which might be changing this, such as the methane concentration. So methane is reacting with hydroxyl. Methane is more than doubled since pre-industrial times. So despite that extra load, that extra burden that the hydroxyl is dealing with, it's managed to keep up. But I think all of the information is useful. We have there in Martin's record useful constraints for the models on the aerosol impact on hydroxyl. So maybe within that, there's also the ability to predict higher loading of aerosols into the future, or less.
All right, I'm very conscious of time. So can we thank the two speakers, and they're both here until Friday.
Yep.
They're up in room 316 or out in the hot desks in front of my office.